that sometimes I forget to hit. Okay, we're recording. That's great. I just sent out an email just now. There was some discussion. I had a meeting this morning with some students. The material on the chi-square, I think things are just pretty crazy right now for everybody. So what I've decided is that the last assignment, because I added it after the midterm, I thought we could get to it, but probably wasn't such a great idea. So what I'm going to do, that assignment is still in Stat Lab. It says chi-square, which that's spelled C-H-I, square, S-Q-U-A-R-E. And there's an assignment there, but that assignment will be optional for you, okay? It won't count against you. I'm going to count it as extra credit. So you don't have to do it at all. If you do work on it, I'll give you some extra credit points for it. And I'll probably do a short video on chi-square because it's a very interesting statistic. Just about everything we've been doing so far has to do with numbers, you know, things that already have numbers attached to them. And statistics works very well on that sort of thing. It's kind of made for that. But chi-square extends the use of statistics beyond things that are already measured or have numbers associated with them into the world of categorical variables, or you could think of it as qualitative things, right, instead of quantitative. But you can still do statistics on qualitative things, right? You can put things in categories, you know, any kind of category, and then you can count occurrences of how many things are in a category, right? So that's one way of approaching it, and that allows you to do some formal statistics on a much bigger area, potential area of problems, right, or real world interests a person might have. It really extends the reach of statistics. There's a lot of statistics you can do on categorical variables, and there's actually a huge branch of statistics that deals with that, and the introduction into that is always this chi-square. There are lots more things after that, but chi-square, it's an interesting tool. So anyway, that's going to be optional. If you do work on it, it'll be extra credit, and it's something that's fun to think about, at least for me. Okay, so it's 12:37. We don't have any more attendees yet, so I'll get started. So you guys get to vote. So what I'm going to do today, I have a really bad habit of explaining things too much because there are key points that I really want to get across to people, and sometimes some students miss those. And so I try to cover those a lot and try to explain, you know, the big picture, the background of what's going on and why you're doing it. And so you'll understand why you're doing the steps you do in these tests. But as a result of that, when I get to work these problems, I don't get very far in actually just, you know, getting the answer and plugging it in the box and going to the next one. So I'm going to back off of the explanations a little bit. I've made a couple more videos. I'll be posting them that have a lot of this explanatory stuff in them. But today I just want to work on problems in the assignment. And this morning I did, I believe it was chapter 8. And I'll be posting that. That will be on Blackboard, so you can watch that video. I worked all the problems in chapter 8. So this afternoon, let's do one of the other chapters. And again, I'm going to try not to go in detail in explaining the whys and wherefores of all the different things that are involved with the problem, but just actually working the problem and getting through a complete problem set. So Would you guys rather that I work on assignment 6 or assignment 7? What do you think?
Could we do a couple on assignment 8?
Well, we can, yeah. We can still do 8. All right, I'll start there. So if you would, just be thinking about which other assignment you'd like to see. But I'll go do some on 8. So let me get that up here, and then I'll be sharing the screen. So just hang on. All right, my stat lab. Okay. And I'm in Chrome, and Chrome, it turns out, is much better than Safari. If you have Safari and an Apple, I would recommend downloading Chrome if you haven't done that already. Okay, assignments.
The problem I was running into was trying to calculate z-scores. I was trying to use the table, but whenever I would like put the answer in, it was wrong, and I can't figure out why.
Well, we'll see why here. Do you remember a particular problem that was on? Did you click on a thing and it showed you a table, or did you get the table from somewhere else?
I used the table from the book.
Okay, let me get the book here. Can you tell me what, have you got that handy? Can you look up what table you're in, what page it's on? And gotta rearrange things just a bit. Okay. All right, I got the book. Which table are you looking at?
I'm pulling it up right now. It was in the appendices.
Okay. Okay, I got an appendix here. So was this a Z? This was a Z-score you were trying to do?
Yeah, and a couple of the problems you have to take the p-value and then find the z-score.
Okay. Oh, it gives. Well, is it? Let's get the actual problem up so I can just be sure about what we're talking about here. So when it says it was an actual p-value, right? It said p-value that it's talking about. Which assignment is that in?
It's in assignment 8. I'll find the problem.
Okay, I'll go to 8 here. This thing's, there we go. Okay, I'm in 8. And you tell me which problem and I'll go directly there. Then I can share somewhere on here. Let me see, share, oh, start video. Let's do that. We are recording. Okay. We like that. Share screen. Here's assignment 8. I'll share that. And then this other.
I think it's number 5, question 5.
Question 5. Okay, let's do it. All right. Historically, percentage of residents of a certain country who support stricter gun control laws has been 53%. Okay, well, wait a minute. Do you see this, my screen? Do you see this problem on your screen now?
Yes, well, no, just the where the questions are, it doesn't actually show the question, like the problem.
Okay, so let me, I want you to be able to see what I'm seeing here. So I gotta get back to the, let's say stop share. Here we go. And reshare. Now, I think right here, and say share. Okay, now you see it?
Yes, and I said it backwards. It wasn't finding the z-score. I had the z-score, and then I was trying to find the p-value.
Okay.
And it wasn't coming out right.
Okay, all right. So I've got the book in front of me right now. And do you have your book?
The one from the online.
Yes. Do you have that? Can you pull up the table? Right.
I have it.
Okay, what page are you on?
I got a lot of screens. Hold on, I'm trying to find it.
So do you have to hang out here today?
It's A3.
Table A3?
Yes.
Or appendix A3?
Appendix A3.
Okay, I've got it. I see it here. Okay. All right, I've got that table in front of me. Now I'm going to read the problem on the screen that we're looking at. Historically, percentage of residents of a certain country who support stricter gun control laws have been 53%. Okay, so that's going to be our null hypothesis, is going to be P, which is a population proportion, is equal to 0.53. All right. A recent poll of 1,095 people showed 536 in favor of stricter gun control laws. Assume the poll was given to a random sample of people. Test the claim that the proportion of those favoring stricter gun control has changed. Okay, so key words here, key phrase is has changed. So we're going to set up a hypothesis test, right? So the null is easy. We've sort of already done that. We say HO, the null is that P equals 0.53. That's the null. So now we need an alternative hypothesis. What's going to be the alternative if the null is not true for the test that we want to set up? The alternative, okay, in this statement here, it says test the claim that this proportion has changed, okay? So the fact that it has changed just means that it is not 53, it's something else, okay? Well, if it's not 53, not 0.53, it is the alternative hypothesis, HA, is that P is not equal to, okay, not equal to 0.53. So that's HA. So I'm going to write that down here. HO is P equals 0.53. It gave us HA is P is not equal to 0.53 because it says has changed. So we know, okay, so we've got not equal to for our alternative hypothesis, okay? So key point about that. So when you have not equals as your alternative, that tells you that you're doing a two-tailed test, all right? The not equal sign means you're doing a two-tailed test. Now this table that we've got here in the book, if you look at it, this is actually a table for a one-tailed test. Because you look at the diagram at the top, it shows Z. And it's good to look at these tables because this is the way statistics used to be done with everything, is with tables, right? And you can still, they're handy still, but you got to know how to use them correctly. So here's what goes on in this table, A3 in the book. What is listed on the left-hand column, okay, is the Z value. And then as you go across the header on the top from left to right, you've got other decimal points, okay? So those decimal points in that header just represent the second digit that's in Z, or the hundredths digit. It's got numbers like 0.00, 0.01, 0.02. So you go down the column, and for instance, let's find Z equals 0.3. So if you're looking up a value of Z, let's say Z is equal to 0.34. What you would do is come down this left-hand column and find Z equals 0.3. Then you would go across the rows looking at the header at the top until you got to 0.04. And what you do is you just add the header value to that value that's in the left-hand column. So 0.3 plus 0.04 would be Z equal to 0.34, okay? So for Z equal to 0.34, you look and see where that row and column intersect, okay? And they intersect, for the example I just gave, if Z was 0.3, okay, let me slow down a little bit. I'm trying to say too many things all at the same time here. But let's say Z is equal to 0.34. Okay, so we look that up in this table, which I just explained how to do. Okay, so we go to the in the first column and find 0.3. Then we look across our header at the top to find the 0.04 because we add those two together. 0.3 plus 0.04 is 0.34. So that's the value for Z. It's those two values added together. So 0.34 is the value for Z, and where the column underneath 0.04 intersects, I should switch the camera on here. I can be pointing at this because I can switch over to this other camera. So let me do that. Taking a long time to make this point, but we never did really look at these tables in class, so it's good to see how this is used. So I'm trying to find, here we go. We got to go up here. Let me move the book again. It's kind of in the way of the computer. All right. Stop share. And now let's, we can enlarge this. Okay, that's what I want. Now I got to move this and this and this and this. So I can get this book over here. This is better. Pictures worth 1,000 words, right? And I lost my pen. Here we go. All right, so in this table, we said just hypothetically, let's say we have a Z value that's 0.34. So here's our Z column. We come down, we find 0.3, then we come across until we get to 0.04. And so where this column intersects with this row, okay, this value here, which you'll see in your table, is 0.6331, okay? So that's the value associated with a Z score of 0.34. Now, what does that mean, okay? If you look at this diagram in the top, again, I said this table is actually for one-tailed test or probabilities. So this table or this diagram in the top, it shows you a Z score here, okay? And then it shows you this shaded area. So this number that we just looked up, this 0.6331, that is the measure of this shaded area. If Z were 0.34, our shaded area would be 0.6331. That's out of a total of 1.0, right? Because the whole area under the curve is 1. So 0.6331 of that area would be where? It would be at our Z value, which we said was 0.34, and include any Z values that are less than that, okay? And this is the standard way that these tables are used. When it gives you a value, that value is called the cumulative probability. So that's a probability if we randomly select a sample, that we'll get a sample at the value that we got, whatever our z-score is, or something less than that. That's the way these standard tables are set up, okay? So these probabilities are the probability of obtaining this z or any z that's less than that z. Now I'm going to go back to the problem that we're working on the computer, our assignment. If I can get back to it here, I think maybe that's it. Okay, we're testing a hypothesis that some proportion has changed, okay? So that means we're testing that the proportion is not equal to this null value that we had here, 0.53. So that means we're doing a two-tailed test, okay? So we can't use this table that we were, well, you can in a different way, but not the way you want to. So let me look and see if there's another table in here. I'm not sure, because I want to do it using the tables and doing it other ways too. Okay, I don't see another Z table here, so we'll use this one. I'll show you how to do it with this table, and then we'll go do it in StatCrunch, and we'll do it there as well. But
That's what I couldn't remember. I couldn't remember how to do it in StatCrunch.
yeah, well, yeah, I'll show you that, but I want you to see how to get it both ways, okay? So let me write this out here, and then I'll switch the camera back. Oh, they gave us, what did they give us here? 0.53. Oh, okay. I haven't actually got to your question yet here, because you said, what was it you said, that they gave us a z and you wanted to get the p-value for it?
Right.
Okay, well, we don't have that yet in this problem. I guess you get it in like part C or D or something. Is that right?
I'm pretty sure it's this problem. I know it comes later. You have to go through so many steps, and then you get to that part.
We'll go through the steps here and get to it then. Okay. So this first thing says population proportion that supports stricter gun control is 0.53. So then I want you to fill in the blank. Well, this P that they're talking about here, and this is unfortunate because in this class, we've got a lot of P's, right? We've got probability, we have proportion, and we have p-value, and those are three different things, okay? But this P it's talking about is it would be better if they wrote a little zero down here, a subscript of 0. And then you could state that as P naught, right, or P sub 0. Anyway, this P is the population proportion, and this is the null hypothesis, so where it's got HO, this would be P sub O, and you just put the same value. It's 0.53, and the alternative is that P sub O is not equal to that value, which again is 0.53. Okay, let's go to the next step. That's all right. Okay, significance level is alpha equals 0.05, okay? And I want to talk about alpha maybe a little later. That's another discussion that's very much related to p-value. We'll get to it. Choose a one proportion z-test and check the conditions. Note the sample's random, observations are independent. So they're telling us that we got random and independent observations. And you have to have those two conditions to be able to use the central limit theorem, right? And also you have to have these sample size conditions on proportions. And the sample size conditions on proportions are I'll switch to the camera again, maybe. Let's see. Yeah, sample size. Well, that's too much to look at, right? Put it over there. There. You got NP has to be greater than or equal to 10, and N times P, N times 1 minus P has to be greater than or equal to 10. And also your N, which is your sample size. Okay, the population size has to be greater than or equal to 10 times your sample size, which is N. These are the three conditions. Three conditions which allow use of the central limit theorem. And a central limit theorem is just a thing that lets us use this normal distribution the way we use it all the time. All these things we keep doing with this normal distribution, where we draw a Z star and we calculate probabilities using that curve, that all comes from this central limit theorem. So you're not allowed to do all that stuff unless these conditions are met when you're talking about proportions, okay? So this is just, and if you don't know what the population proportion is, which here we're given a postulated one, right? We're given the null hypothesis. They're claiming it's 0.53, so we can use that as P here. Or if you actually know the true value, you would put it in here, okay? If you don't know it at all, if you have no clue what it is, you could use P hat, which is your sample proportion. But anyway, these are the three conditions. So just your sample size N times the proportion, that number's got to be greater than or equal to 10. Your sample size times the quantity of 1 minus the proportion has to be greater. Oh, I miswrote. This is supposed to be 10 also here. It should be greater than or equal to 10. And then your population has to be at least 10 times bigger than what your sample size is. All those are met. You're allowed to do what we do with all this normal statistical tests we do with the normal curve in proportions, okay? Let me go back. Okay, and so here they're just asking us to do the arithmetic. They show you, here's one of the conditions, N times 1 minus P, okay? And you just calculate that and plug it in here. So it tells us, and what's N? N is your sample size. So up here we had a poll of 1,095, so that's N. That's how big the sample is, right? So it's 1,095 times 1 minus this, or it'd be 1,095 times 0.47. So let me do that on the calculator. 1,095 times 0.47 equals, okay, it's, I'd round it off to a whole number because it says about, so that's 515. So we're way bigger than 10, so we're okay, which is more than, what's going on here? Oh,
I think it's 10. I think you put 10 there.
I was reading this, and because I saw that period, I thought it was, okay. Yeah, so 515 is more than 10. That's one of the conditions. N times 1 minus P's got to be greater than or equal to 10. That's way bigger. We're good. Round to the nearest, okay. This morning I made like 3 errors because I put these numbers in too fast. I didn't slow down and read, you know, carefully enough. Anyway, check answer. Okay. All right, compute the sample proportion. That's just, we got 536 out of 1,095. That's a proportion. It's just a ratio of successes out of the total. And so here we're calling somebody that supports stricter gun law, we're calling that a success. Or it could be yes or no's, but it's just that ratio, 536 divided by 1095. Okay, and I get 0.4895, and it wants 4 decimal places. Okay, so 0.4895. Okay, and that's called p hat. That's the sample proportion. Okay, so we're good there. Now it says calculate the values needed to compute the standard error. So for proportions, and here they've got p naught, okay? So that's our null value, or our claimed value for the population proportion. You just do this arithmetic. So this is PO times 1 minus PO. And we know PO was 0.53, so 1 minus PO is going to be 0.47. And they're showing you that right there. You just plug the number in, right? Although it being a test, that's probably reason enough to make you paranoid and think, oh, maybe it's something else that's too easy. And then you stress out over it. But okay, compute the standard error. So that just says do this calculation. This is the standard error, this thing. So we just do this calculation, okay? So 0.53 times 0.47 equals divided by 1095 equals, and I get 2.275 times 10 to the minus 4. So let me put that in again. Second square root of it just now occurred to me, I know I don't have a class of people here, I just got 2, but some people may actually want to see what keys you type on the calculator, but everybody knows how to do this part here, is that right? How to put it in your calculator. So 0.0002275, okay, square root of that. And I get an answer, and it wants 4 decimal places in the answer. So to 4 decimal places, it would be 0.0151, 0.0151. Okay, likes that. Let's go next. Okay, identify the values needed to compute the Z test statistic. Okay, this is the formula. This is the formula. This is your test statistic here, okay? It's p hat minus the null value, the claimed value, divided by the standard error. And remember, this is like a count of how many standard errors this difference is, right? If you divide this difference by some set amount, you're saying how many of these amounts make up this difference. So that's Z score. This is a test statistic, but it's a Z score. So it's a number of standard errors. And the standard error is just really, it's the standard deviation of these things. If you did this over and over and over again and got a different p hat each time, this would be the standard deviation. It's the size of the standard deviation of the p hats. If we were dealing with means here instead of proportions, this would be x bar and this would be mu over here. But it would be the same thing. You'd have standard error down here. Standard error has got a different formula for means than it does for proportions, but it's the same equation. It's the sample value minus the null value divided by the standard error at Z. So we put that in here, and we can scroll up because I don't remember what they are now, but we already got what p hat was and put in here. P hat's 0.4895. So 0.4895, and p naught is the null hypothesis. We were saying it's 0.53. And the standard error, here we don't have to do the standard error. They're just wanting those two values. I'm trying to get this thing to scroll here. Why is it not scrolling? There. Why is it stuck? I clicked outside of it. It should scroll. Okay, type the term. Oh, I got to hit enter, I guess, maybe. Oh, I got to hit check answer. All right, check answer. There we go. All right. Okay, compute the Z statistic. So we just do this. We need the standard error. Okay, and we have it. We did it earlier. Also, let me go back up here. We put it in there already. Standard error is equal to 0.0151. All right. So compute Z. So we just do this calculation that's up here above. So we say 0.4895 minus 0.53 equals, divided by the standard error, which we said is 0.0151. And what we get is round to 2 decimal places, so minus 2.68, okay? All right, now I'm going to pause here for a second. So this Z is called a test statistic. That's because it comes from the sample, right? Well, why do you say that? Because we had to have p hat, which is the sample value, in order to calculate what Z is. So in all these tests, there's always two of the distribution you're talking about. There's two values. There's a critical value, and then there's a value you get for your sample. And that's what the test is. You're comparing your sample value with the critical value to see, is the sample a more extreme value than the critical value or not? If it is, if the sample value is more extreme than the critical value, you reject the null. And what does more extreme mean? More extreme means the distance to the proposed population parameter. Here, the population proportion, that the distance from your sample to that proposed, or to the null hypothesis proportion, is bigger than the number is for the critical value. So, for example, we've said a bunch of times, like at a 95% confidence level, the critical value for Z is 1.96. So that's saying if you are more than 1.96 standard deviations, or standard errors, which is what this is, if you're more than 1.96 standard errors away from the mean, you're going to reject the hypothesis. Okay, so if we were doing a 95% test, which in this problem we are, because up above it says perform a hypothesis test using a significance level of 0.05. Well, that tells us we're doing a 95% confidence level, because confidence level equals 1 minus significance level, and vice versa, okay? So this is like, you can think of this as just how many standard deviations away from the mean. And when I say mean, I shouldn't say mean, I should say this PO in this case, because we're doing proportions. This is how many standard errors, which are standard deviations, how many standard errors or standard deviations are we away from this value. And so when this is a big number, we're going to reject the null. If it's not a big number, we're not. And what's big? Bigger than the critical Z. And a critical Z is just a function of what confidence level we're testing at. If it's 95%, critical Z is 1.96. Is this bigger than 1.96? Okay. A word here, remember we're doing a two-tailed test. So in the picture, you have a Z star that's 1.96. That's a positive number. But you also have a negative Z star, So it's minus 1.96. So a value more extreme than Z star means it's either greater than positive 1.96 or it's smaller or less than negative 1.96. So this is over in the left-hand tail, and it's past the negative 1.96, okay? All right, so let's move on. Okay, and here we are. We finally get to the table, which is what was throwing you here. Okay, so we've said you can't use this table. You can't just put Z in and get this value here. So now I need to do a drawing, but I think we can use this table, but we have to do it a different way. All right. Let me make a drawing, and then I'll switch the camera over. Okay. Let me scroll back up here, if it'll let me. Oh, okay, so that's our Z is minus 2.68. Okay, and our critical Z, I'm gonna do it different. Let me redraw that so it's clear. So we're testing at a significance level of 0.05. So our Z star, our critical value of Z, is 1.96, okay? 1.96, which means we've got a negative Z star. We've got a tail on the other side because it's a two-tailed test. So this value is negative 1.96. Okay, and we want to know, in this problem, we have a Z write this down. Z equals negative 2.68. That's our actual, our test statistic, our sample, okay? All right, and we want to know what the p-value for that is. The question, what is the p-value for Z equals minus 2.68. Now let me grab the table here. Okay, and I get probability equals 0.9963. Okay, this is, all right. Got to make a couple drawings here. Let me show you what this means. Z equals 2.68, and the probability, which I'm going to draw that in here, okay, equals, what did I say it was? 0.9963. Okay, I'm going to switch the camera over to this now. Are you still with me?
Yes.
Okay, good deal. Where? Okay. So first, the top diagram. We're doing a two-tailed test, right? In this problem that we're doing, because the alternative hypothesis was not equal to, so we're doing a two-tailed test. And I was using this earlier as an example. At a 95% confidence level, our Z star, we know is 1.96, okay? And here's the Z that we got for our sample. We got this value here, minus 2.68, right? So that's minus 2.68 standard errors, if you will, okay? These are standard errors from the proposed null population proportion, okay? So this is the null proportion for the population, and our sample came in at minus 2.68 standard errors, which are standard deviations, below this value where the null population occurs, okay? And the question is that it's asking us is, what is the p-value for this, okay? Well, here's what p-value is. P-value, and this diagram isn't great here, but it would be the probability. This should be dropping off here. I didn't draw that very well, right? This tail from this curve should be just dropping off. So the p-value is the probability that you'll get a value that you got for your sample, which is this value, or a more extreme value than that. What's more extreme? Something further away from this mean than your sample was. So all of these values over here are more extreme, okay, than your sample is from here. So the p-value is this probability in this tail. Okay, but since we're doing a two-tailed test, the p-value is actually that probability and its mirror image. So, because you could have got, okay, we got a minus 2.68 for our sample, right? But since we didn't know if we were above or below it and did a random test, you know, we could have got a sample exactly on the other side, that this would have been this Z here would be 2.68, okay? And so the p-value, it'd be easier to explain with the one-tail test. I think I'll do that, and then I'll come back to this because it's a little confusing with the two tails. And there's just no easy way to, once you understand it, it makes sense, but it is confusing for anybody. Even once you understand it, when you think about the two tails, it's a little confusing. So I'm gonna show you a one-tail example of what p-value is, okay? And then I'll go back to our test, which is a two-tailed test. But so you understand what p-value is. So in a one-tailed test, you have a critical Z value, which comes from whatever confidence level you're testing at, okay? So that defines the threshold for your test. You go, okay, and I'm going to use a 95% confidence level here, okay? So at 95% confidence, alpha is equal to 0.05 because alpha equals 1 minus the confidence level, okay? The confidence level would be 0.95, or the probability is 0.95, okay? So you have a Z star for that. Now, since this is a one-tail test, this Z star won't be 1.96. It'll be slightly different from that, okay? But don't worry about what this, now you can look, and we could look this number up from the table very easily. That's what the table's made for. Matter of fact, let me do that. Let me put that in on this one-tailed test. So, I use the table backwards. I try to find 0.950 value in this table of values, and here I'm real close to it. It's between 0.4 and 0.5, so that's 1.604. So 1.604. I'm going to say roughly 1.0. Is that right? No, not 1.0. It's roughly 1.6. 1.6. Yeah, 4, 5. Okay, so it's approximately that. Anyway, that's approximately right. And I got that from the table. So that's this Z star. That's a critical value. So for 95% confidence, okay, so 95% confidence means that alpha equals 0.05. Well, alpha is just this area here, okay? It's the probability of a randomly collected sample being outside of this threshold. So it's being the threshold or worse than that, okay? So it's all this probability out here. That's 0.05, and that's alpha, okay? So p-value, this all just has to do with our confidence level, and we look this up or get it from a computer. It has nothing to do with our sample. This is the threshold for the test. And so before we get a sample, all right, think about this. If we get a sample and it occurs outside this threshold, that's a low probability event, right? Because there's less than a 5% chance we'll get something at this value or above it if we randomly get a sample, okay? And what happens if we do get something above here? If we get something above here, we're going to reject the null hypothesis, which says that this value is what it said it was, that this value really does live here in the middle, okay? We're going to reject that and say, well, this probably isn't right because we got a sample way out here and there's a very low probability of getting this sample if this is true. So therefore we reject this, okay? That's the outcome of the test. But when we do that, okay, there's a 5% chance that we're wrong, okay? That's what this alpha equals 0.05 is. It means if we get a sample out here anywhere in this area and we reject this at this level, at the 95% level, we reject this, it's 95% chance we're correct in rejecting it, right? Because it's a low probability that we would get this if this is true. But there's a 5% chance that this is that you would get a sample out here when this really is here. Okay, it doesn't happen often, but it does happen. So basically, this is called your significance level. Alpha is called the significance level. But it's also called your type, and you see this again, type 1 error rate. Okay. So a type 1 error is when let's say that the real parameter is here. We go out and get our sample, and our sample hits right here, okay? So we say, oh, we're past this critical value, so we're going to reject the null. We're going to say, no, this isn't true. That isn't really where it is. Well, if it is true, then we've made an error when we reject it. We reject it, but it was true. That is where the real thing is. So we made an error there, and there's a 5% chance that we'll make that error, right? Because 5% of the time, if this is the real value, you will get a sample that's way out here. It's not often, it's rare, but you do get them, okay? So that's alpha. So p-value, which is what I'm trying to get to here, p-value, this is your sample statistic here, okay? This outside one. P-value is this probability. It's the probability of getting the value you got for your sample or something more extreme than your sample. And what's more extreme? Something further away from the proposed value. So this area in here is called your p-value. Okay? This area from the critical statistic, Z star, or if you were doing a t-test, T star, the area outside of Z star, from Z star and above, this whole area, this is alpha. And this is determined by whatever confidence you want to test at. There's a different alpha. You know, you give me the confidence level, I subtract that from 1. That's what it, so at different confidence levels, your Z star is in different places. That's all that's going on there, right? This is a common one that's used. And then we get a sample and we look to see what's the probability that we'll get a value at the value we got for our sample or something more extreme than that. And that probability is the area in this tail that's beyond the sample. And that's the p-value, okay? So then when we do a statistical test, we compare the p-value with alpha. If p-value is less than alpha, reject, null. Okay? So alpha is this area. So if we get any area that's less than this area, so if our sample falls anywhere past this critical Z, if it falls anywhere past this line, we're going to reject the null because our area here is going to be less than alpha was. So that's what p-value is, okay? But now when we're doing a two-tailed test, which is what it's the same thing, it's just there's two tails involved, okay? So a two-tailed test, here's a Z star. So we have a negative Z star. So when you say alpha equals 0.05 on a two-tailed test, alpha is made up of both of these areas, right? So this 0.05 is both of these areas added together to give you this probability. Okay, there's still a 5% chance you'll be outside of Z star, but it's a 2.5% chance you're above positive Z star and a 2.5% chance you're below negative Z star. But it's a total of 5% that you're outside, you know, that you're outside of this region, which, you know, they do in red and StatCrunch all the time, right? 5% chance you're outside that. You could be in either tail. And and it's symmetrical, so there's 2.5% of the areas here and 2.5% here. So when you get a sample and you want, in our case, our sample was minus 2.68, okay? Z, that's the sample. And this is minus 2.68, all right? And here's a Z star. this is minus Z star, and this is plus Z star. And this is Z equals this, okay? I should write that down here, just Z equals, okay? So this is our sample right here, okay? The p-value then is this area here plus if you had the same violation on the other side, okay? So this, if this Z is minus 2.68, then this value would be plus 2.68. And it's this area plus this area. Those two areas together, those two probabilities together make up your p-value. Okay. And here, if we're testing it to 95, alpha is just like we did in this upper, in this diagram here. Alpha is still the same. Alpha is this whole area past Z star. So 2.5% of the area of this whole curve is in here, 2.5 is in here, from negative Z star back. Is this helping you? Hello?
I'm here.
Is this helping you to understand what p-value is?
Yes.
Okay, so we understand on a two-tailed test, to get p-value, we get the area that's past where our sample statistic was, that's more extreme than our sample statistic was in relation to this mean. But since it's a two-tailed test, we have to double it, because the test just means the chances of getting something more extreme than your sample. More extreme mean at that distance from the mean or greater. But that distance could have been in the other direction too, right? Here's the same distance the other way or greater. So we have to add both those areas. So that's what p-value is. Now, getting back to this table we were looking at, okay? The problem, the way the table's set up, the table is always set up, usually they're set up for a kind of a one-tail thing, okay? So the table has a Z value. This is for the table, okay? It just gives you a Z. And you've got this grid, right, of numbers in a table. And basically you just look up a value in that table, right? You look up Z and you get part of the Z from here and part of it from here, but you're just looking up what Z is, a value for Z. And this is a probability. The value it gives you for that Z is a probability, okay? This probability that comes from the table is always the probability of getting the Z that you looked up. So this Z here and this Z here, right? That's where they intersect. So we looked up this Z and got this value. So here's the Z, and the probability that this table gives you is always the probability of getting this Z or something less than that Z. So it's giving you this total area here on out forever this way. It's called a cumulative probability, right? It's the cumulative probability of getting anything from where this thing first begins, way out here in the tails, all the way up to this value. So that's the table value, all right? If we're looking up a p-value is a probability, but it's a different probability. If it were a one-tailed test, the p-value would be this. Which way to draw that? That way or this way? Let's go this way. Let's draw it that way. So differentiate a little bit more maybe. Okay, so this is the p-value for a test. It's a value that's at that value or more extreme, right? Well, the table's always giving you the cumulative up to that point. So if it were a one-tailed test, we would get this by saying 1 minus the probability, which is this thing here, right? Is this whole area in here, which is your table value. Table value. So 1 minus this table value of probability gives you this probability, which would be the p-value for a one-tailed test. We are doing a two-tailed test in our problem. So we can still do it. We just have to remember that we're talking about two tails. So our sample statistic was minus 2.68. Okay, so if we want to use the table's always set up where the z number is a positive number, right? So to use the table, we look up the value for 2.68 because that's a positive number. And what's that going to give us? When we look up the probability associated with this z, 2.68 in the table, it's going to give us the probability of this whole curve from 0 or negative infinity all the way up to this point, okay? But we're trying to get the p-value, okay? So, but we know the p-value is actually, it's both of these areas combined, right? It's the probability of getting the value you got or something more extreme than that. So if we look up in the table for this z, table value is a probability, okay, probability. And that is, this. But this is the whole thing. It's all this area. It's everything back from where your sample is, okay? We're trying to figure out what these two together are. So what we do, we can get this one real easy. We can just say 1 minus the table value. And that gives us the probability of being in this right-hand tail, right? Equals the probability that you're in right tail. So we just look up in the table this z value. That gives us the probability of everything up to this z. We subtract that from 1, and that gives us what's in this right tail. But for a two-tailed test, the p-value is the probability that you're outside of it either way. If it were a negative value, what's the probability you're out? So you have to add these two areas. So what we do is we just double this because it's symmetric. If we figure out the area of this tail, this being more extreme on the other side is the same probability because this is a symmetric thing. So we just say 2 times this area here, basically. I don't know if I can't draw a good arrow to that. 2 times that area. Okay. 2 times this area here. 2 times right tail, which is past your sample value, past sample value, equals p-value. So it is a probability, okay? And tables always give you put a z in a table and it always gives you the probability of anything up to that point, the whole curve. It's not looking at all this stuff here. It just says, okay, I've got a curve that goes up to that point. And for that z, it gives you the area of everything below that point. So to get something above that point, we say 1 minus this. That gives us the area above it. And now, since we're doing a two-tailed test, we have to double this value, because two-tail means it could have been over here also. It could have been that extreme and over here. Okay, hopefully that makes sense. So from this table then, we look up the value for 2.68. I think, didn't I do that already? Let's see. Maybe I did, and I don't know if I wrote it down. Okay, using your table that you want to use. So let's take 2.68. Here's 2.6. I don't know if you can see, it's not focusing very well there. Anyway, you go in this table, you get the general idea. You come down to the z's, the 2.6. You come across to the, what was the number? 2.6, what? 2.68. So 2.6, we come across to the 08. And and that means we've got 2.68 for a z value. Our probability is 0.9963 is what that value is, okay? So, all right, here was their z equals 2.68, and the probability from the table, and that's a one-tailed table, was 0.9. I looked it up and set it, and now did you write it down there?
Yeah, it's 0.9963.
9963. Okay. So what we do is so that's this probability. That's everything up to that point. So we take 1 minus 0.9963, and that would be a 737. That would be right 0.0037, right? So this is the probability that's in this tail here, that's beyond that z value. But we want the p-value for a two-tailed test. So we got to say, okay, this was 2.68. This is minus 2.68. So the p-value should be 0.0037 times 2, okay? So it should be 0.0074. That's the p-value for a z equal minus 2.68. All right, let me go back to the screen there, the sample. I think that's it, hopefully. We've taken a while. Yeah, I know. I'm windy. Okay, p-value. How many decimals it wants? 3. So that'd be 0.007. 0.007. Enter. It likes it. Okay. Makes sense?
Yes, I just wasn't subtracting it from 1 and then doubling it. So I understand where I was going wrong now.
Okay. All right. Good deal. So you want to continue with these problems here, or you guys got another problem you want to look at?
That's all I have.
Is that Tinley that's talking there, or Shayna?
Shayna.
Shayna. Okay. Tinley, do you have anything else?
I haven't really started on assignment 8. I was planning on doing that on the weekend.
Okay. Well, I can work another problem or two if you want me to. I don't have anything I have to do right now. Let's see, I think, yeah, I got another call coming in at 3 that I'll be with them a long time. So you want to work another problem or two, or are you good for right now?
I'm good for right now.
Okay, good deal. Well, let's see. Okay, I mentioned that the chi-square's going to be extra credit, right? I said that at the beginning.
Yes, will those be on the final?
No, They were. I actually rewrote the final. I spent a while doing that, but I'll rewrite it again because it was wishful thinking. I thought I could cover all that before then, but I'm not getting there. So I will cover it, but it's not going to be on the test. So you don't have to worry about, you don't have to stress over chi-square. But again, it will be extra credit. So the homework assignment's in there, which won't hurt you if you don't do it. That's not going to penalize your grade. If you do it, I'll give you some extra credit for it. And I'll take the questions off of the final that were on there about chi-square, okay?
Okay.
But yeah, it's a good thing to have some familiarity with because it is very useful. And if you ever end up doing any statistics, you'll end up using it, okay? Well, if you guys don't have anything else, I'll get moving here. I'll try and get productive. So have a great day, stay safe, and enjoy the sunshine if you can, all right?
All right, thanks, you too.
Yeah.
All right, thanks.
See you later.
See ya.
All right, I got to stop share and end meeting and